Today, I want to talk about pointers and how we can use them. So, by definition, we say a pointer is a variable that contains a memory address. It means the pointers, they can hold addresses. In C++, we have something that we call a dynamic memory allocation. In this example here, you see that we're defining a vector of 5 integers. With vectors, you could dynamically allocate arrays. It means you can create a data structure that can grow and it can shrink. So in this example here, I say the first one in the vector becomes 9, second one 1, third one 6, 8, and 3. If I use the cout and I use the size function, with this size, I can get the size of the vector. I would have a vector of size 5. So it will show size 5. If I push back 2, I can add another element to the vector. The size becomes 6. If I call the size function again, the size becomes 6. You can see that the vector uses a dynamically allocated array, an array whose size can change during the runtime. In order to create a vector, you say vector, you put the data type in brackets, you put the name of the vector and how many elements you have. You could initialize the vector using .at. In this example, using .at, I'm putting 5 different numbers inside my vector. With the size function, you can print the size of the vector. You could insert and erase vectors very similar to the linked lists. So in this example, we have a vector. You're looking at the insert performance problem. When you say user_insert, user_get begin plus 229, you're trying to insert an element inside the vector. If you want to insert something inside the vector, you have to move anything else 1 forward. So when you say insert user grades dot begin plus 229, it means you want to insert 29 here inside the vector. There's a problem here that means that you have to shift everything 1 forward, which will be time consuming. So we can say vector is very similar to array in sense that vector is different than array because it can grow or shrink. But the way that we store the elements inside the vector is similar to the way that we store elements inside an array. So this problem here, we call it vector insert erase performance problem. It means whenever you want to insert or remove something from a vector, it's very time consuming. You have to shift everything, which is very time consuming. We have another data structure that we call a linked list, which I'll talk more about. So inside the linked list, we can insert elements much faster and easier than a vector. Linked list is a data structure that is created using pointers, which the pointers are some variables that they can hold addresses. In this example here, you see inserting a new item B between A and C just requires changing the A's to point to B's memory location and B to point to C's location. If you want to insert something inside the linked list, it's very easy. In this example, we have a linked list, which inside it has nodes A and C. The address for node A is 86. You can see the data, the next for the node A is 88. It means that it has the address of the next node. If you want to insert something inside the linked list, it's very easy because you can just put the address of C inside A. It means after A, we have C. If you want to put B between A and C, we can just make the A to point to the C. We can just make the A to point to the B and then B to point to the C. It means the A next will have the address of B, and then the B's next will have the address of C. So by changing these pointers, we can insert an element inside the linked list easily. If you want to compare vectors and linked lists, vectors are very similar to linked lists. We can store items in continuous memory locations in Victor using Victor. It supports quick access to id element using @I. It may be slow for insert or erase on large lists due to necessary shifts of elements. If you look at the linked list, we can see that it stores each item anywhere in the memory, with each item pointing to the next item list. It supports fast inserts or deletes. You can have access to id element may be slow because you have to traverse from the list item to the id. It uses more memory due to storing a link for each item. With linked lists, we can easily insert or remove something. With Victor, insertion and removal can be time consuming. So I want to talk about pointers. We have something that we call it this. This is a keyword. In this example here, you see we have a function set side length. It has a side. When you want to put the side inside the side, we say this, we put an arrow. This is used to distinguish this variable from this variable. It means I want to put the current object's side length, I want to set it to side. We can say that this pointer enables access to an object's data members within the object class member function. So with this and member access operator, this arrow, we call it member access operator, we could access different attributes of an object. When you say this side length, it means I want to access the side length of that current object. In C++, you can define pointers. So we say a pointer is a variable that holds a memory address rather than holding data like most variables. In order to define a pointer in C++, we use this notation. We say int star max item pointer. This will declare an integer pointer named max item pointer. We can say an integer pointer holds a memory address of an integer, and a double pointer has an address of a double. So we have something that we call the reference operator or ampersand, which it obtains a variable address. For example, ampersand somewhere returns the memory address of variable somewhere. In this example here, we have a variable. We say int some point, that's a variable. Int star val pointer, you're defining a pointer to an integer. When I say sum int equal to 5, I'm putting 5 inside this sum integer. With ampersand, you can get the address of this sum int. When you say cout ampersand sum int, it will display the address of that variable, which is 76. If I say val pointer equal to ampersand sum int and I print cout val pointer, it displays 76. In order to define a pointer in C++, we can use this notation. This means I'm defining a pointer to integer. So when you have a pointer to integer, it can hold an address of an integer variable. When you say ampersand, it means I want to get the address of this current variable and I want to put it inside this pointer. When you want to display a memory address, we usually use a hexadecimal value like 006FF978 or 0x7FFC. These are hexadecimal values, which is base 16. So base 16 is used to represent the addresses. You could use dereference operator to dereference a pointer. It is prepended to a pointer variable's name to retrieve the data to which the pointer variable points. For example, if val pointer points to a memory address containing integer 123, cout double left arrow star val pointer will dereference the val pointer and output 123. With this star, you could dereference a pointer. It means it will give you the actual data that you have in that pointer. It means it will take you, this star will take you from a pointer to what that pointer is pointing to. In this example, I have an integer sum int. I have a pointer to integer. I say sum int equal to 5. This integer variable becomes 5. I say cout sum int address is ampersand sum int. This ampersand, it means I want to get the address of this variable and I want to display it. The address sum int has is 76. You can see this 10, the address is 76. If I say val pointer equal to ampersand sum int, I'm getting the address of this variable and I'm putting it here. I'm displaying it. It says the val pointer is 76. I can say cout star val pointer. This star will take you from a pointer to what that pointer is pointing to. So the star val pointer is 5. I can say star val pointer equal to 10. This dereference operator is used to take you from a pointer to what that pointer is pointing to. 10 will go inside what this pointer is pointing to. When I say cout sum int, it will display 10. When I say cout star val pointer, it will display 10 again. You can see that with the star, we can dereference a pointer. This is how we can define a pointer. With ampersand, you can get what that pointer is pointing to, which is the address of that sum int. With the star, you can dereference a pointer. It means it can go from a pointer to what that pointer is pointing. You could also have null pointers. When a pointer is declared, the pointer variable holds an unknown address until the pointer is initialized. If you have a pointer that is pointing to nothing, we call it null pointer. Null means nothing. A pointer that is assigned with the keyword null PTR is stated to be null. For example, int star max val pointer equal to null PTR. It makes the max val pointer null. In this example here, you see that we have a function. This function is taking an integer pointer. I say if value pointer equal to null PTR, cout pointer is null. Else cout star value pointer. I'm defining an integer variable. I am putting 5 inside. I'm defining a pointer to integer. I am putting null inside it. When I call this print value with val pointer, since this is a null, this condition will become true. It will display pointer is null. When I say val pointer equal to ampersand sum int, I'm getting the address of some integer. I'm putting it here. When I call this function, this will not be null, and it will display what that pointer is pointing to, which is 5. So null PTR was added to the C++ language in version C++11. You can see that this null PTR is something new that they added to the language. Before that, in the C, we used to use null to indicate null pointer. There are some activities in this chapter I want you guys to finish. There are some number of common pointer errors, so don't make these mistakes. One common error is to use the dereference operator when initializing a pointer. For a variable, for example, declared int max value and pointer declared int star val pointer, if you say star val pointer equal to ampersand max value, that is a syntax error. Because a star val pointer is referring to the value pointed to, not the pointer itself. This is an example that it shows this is a mistake that some programmers do. When you define a pointer, this is a pointer. The pointers, they can hold addresses. When you say star val pointer, it means you're dereferencing that pointer. What you put here, it has to be a value. When you say ampersand, it means you're getting the address of this variable, which is wrong. So don't make this mistake. Another common error is when declaring multiple pointers on the same line. If you forget a star before each pointer name, for example, int star val pointer 1, comma val pointer 2, it will declare val pointer 1 as a pointer, but val pointer 2 is also declared as an integer because there is no star before val pointer 2. In this example, you're defining a pointer, but this one is not a pointer. Val pointer 1 is a pointer because you have a star here, but the second one is not a pointer, it's a regular integer variable. There's a good practice to declare one pointer per line to avoid accidentally declaring a pointer incorrectly. Some common runtime errors include, for example, when a pointer has not been initialized. If you have a pointer that has not been initialized, if you say cout star val pointer, it may cause a program to crash if the val pointer holds an unknown address or an address that the program is not allowed to access. When you want to use a pointer to dereference a pointer, remember that that pointer has to point to something. If you have a pointer that doesn't point to anything, or it doesn't have a memory location pointing to, then you will have an error. There's a common error to dereference a null pointer. If a val pointer is null, cout stall val pointer will cause the program to crash. A program should always hold a valid address before pointer is dereferenced. When you want to use this star, remember you're trying to dereference. When you want to dereference, you need to have a valid pointer that points to somewhere. These are some examples that shows these errors. I want you guys to finish these activities. There are two pointer declaration styles. Some programmers prefer to place the asterisk next to the variable name when declaring a pointer. Some programmers, they just say int star val pointer. So some programmers, they say int val pointer 1, comma star val pointer 2. It's a good practice to use the same pointer declaration style during your code. Like, for example, either int star, like this star, you see there's a space after that. Some programmers, they put the space before. Some programmers, they put the space after. So whatever you do, try to be consistent. In this class, in this Zybook examples, the style that is being used is with a space here, which will declare one pointer per line to avoid declaring a pointer incorrectly. I want you guys to finish these challenges activities. Finish all of these. In C++, we have some operators like new, delete. With new, you can allocate memory. We say the new operator allocates memory for the given type and returns a pointer to allocated memory. If the type is a class, the new operator calls the class constructor after allocating memory for the class. So with the new operator, you can allocate memory. In this example here, we have a class point. In this class, we have a point constructor. We have double x and y, which there are two different variables. You can see at the definition declaration of the constructor, which this is a default constructor, I'm putting 0 in x and I'm putting 0 in the y. When I say point star sample equal to new point, with the new operator, you're allocating memory for a point. This sample is pointing to that object. So when you say new and you put the name of a class, the constructor runs. When the constructor runs, this statement gets printed. X and Y becomes 0. After that, you display exiting main. This line will get displayed and the program ends. In this example here, see, with the new operator, you can create an instance of a class. When you create an instance of the class, the constructor runs. When the constructor runs, it will display this message, and then x and y, they become 0. You could have constructor arguments. The new operator can pass arguments to constructor. The arguments must be in the parentheses following the class name. In this example, we have a class point. It has a constructor that makes the x value 0 and the y value 0. It has a print function and it has two double variables of x and y. When I say point star point 1, I'm defining a pointer to a class. When I say new point, I'm creating an instance of this class. When you create an instance of this class, you can see this class has a constructor. So the constructor takes two default values of 0. The constructor will put x value inside x and y value inside y. When I say start point 1 dot print, I'm calling the print function. If I just say new point and I call the print function, it will display 0 and 0. It means I'm using the default constructor to create an instance of the class. If I say point star point 2 equal to new point 8 comma 9, I'm creating another instance of the class. I'm using 8 and 9. When I use 8 and 9, I'm putting the 8 and 9 inside the x and y. It means I'm creating another instance of the class that the x value, the x is 8 and the y is 9. So when you say new, you can create an instance of a class. What you put after this, if you put something in the parentheses, the compiler will pass those values to these arguments, and it would create an instance of a class with those specific values. We have something we call the member access operator. This. To use, when using a pointer to an object, the member access operator allows access to the object's members with the syntax A pointing to B instead of star A dot B. If my point is a pointer to a point object, my point and arrow print will call the print member function. So with this member access operator, you can use a pointer and go from what pointer from what you want to use, what you want to call from that pointer. So in this example here, you want to display points 1, y's member value without cout. You can say cout star point 1 dot y. It means I want to go from this pointer and I want to access y, which point 1 is pointing to the y. You can also use it with member access operator. You can say cout point 1, and then you can use the member access operator and you can put y. It means I want to go from this pointer to the y, and then I want to print it. You can call points to print member functions. You can say star point 2 dot print. So this will call the print function, and you will dereference the pointer to access and call the print function. You can also use the member access operator. You can say point 2 member access operator print. It will call the print function from that point 2. There are two different ways of using pointers. One of them is to use dots. One of them is to use member access operator. With member access operator, you can access different things that the pointer points to. We have another operator in C++, which is a delete operator. The delete deallocates or frees a block of memory that was allocated with new operator. If you say delete pointer variable, you will deallocate the memory. It deallocates the memory block pointed to by pointer variable. If pointer variable is null, delete has no effect. After the delete, the program should not attempt to dereference pointer variable, since the pointer variable points to a memory location that is no longer allocated to use by the pointer variable. Dereferencing a pointer whose memory has been deallocated is a common error and may cause a strange program behavior that is difficult to debug. So when you say delete, you're deallocating a memory. When you're deallocating memory, there's no memory allocated. You couldn't use a memory that is not allocated. If pointer variable points to deallocated memory that is later allocated to some variable, changing star pointer variable will change some variable. Calling delete with a pointer that wasn't previously set by the new operators as undefined behavior as logic error. This is an error, don't do that. If you try to use the delete with a pointer that was not specified and allocated with a new, you will get a logic error. Whenever you have new and delete, I mean, if you want to delete something, you need to first create it using new. These new and delete, they go together. With new, you allocate memory. With delete, you deallocate. In this example, we say point star point 1 equal to new point, 7, 3, and 19. With the new operator, we're allocating memory for a point object. We have a pointer that points to a point. When you say new point 73 and 19, point 1 is allocated and x, y members are displayed. X becomes 73 and y becomes 19. If you just say point 1 and then this error X, it will display 73. If you say CL 0.1, you put error Y, it will display 19. If you say delete 0.1, you're deallocating the memory. It means that memory doesn't exist anymore. If you try to call this print function using 0.1, that will cause a problem, which is an error. Since 0.1 points to deallocate memory, attempting to use 0.1 after deletion is a logic error. This will not work. You will get an error. You could allocate and deallocate object arrays. The new operator creates a double allocated array of objects. If the class name is followed by square brackets containing the array's length. So if you want to allocate memory from sequences of data, for example, in this example here, I say int point count equal to 4. I have an integer variable which is 4. I say point star many points equal to new point count. I'm allocating memory for an array of 4 integers. I say for int I equal to 0, I less than point count plus I. My points I dot print. I'm calling the print function for each element inside my array. When I use the new operator, I'm creating an instance of this class. So when I create an instance of a class, I get 4 objects, which all of them, they have X and Y of 0. If I use this for loop to display them, I'll get bunch of zeros and zeros, which are 4 zeros and zeros. Because I have 4 objects that each one has X and Y that are zeros. If I say delete many points and I open and close brackets there, the entire array is freed with the delete operator. It means with delete, I can deallocate all of this array. This is how you can allocate memory for consecutive memory locations. When you use the delete operator and then you want to deallocate an array, you open and close brackets after delete. I want you guys to finish these activities. You could have a string functions with pointers. The C-string library introduced contains several functions for working with the C-strings. So if you want to work with the C-strings, you can say hashtag include C-string. We have some functions in the string library that in the C-string library, like strcmp that will compare two C-strings, like strcpy that will copy one C-string inside another C-strings. There's an example in your Zywick that shows how to use this. In this example here, I have a C-string of size 10. I'm putting A, B, C, X, Y, and Z. I have another C-string that is as X and Y and Z. I have another C-string that is size 10. There's nothing in it. I have a pointer to a character that is null. It's initialized to null. When I say strcmp, a string 1, a string 2, it means I'm comparing a string 1 and a string 2. And I'm putting the result inside this CMP1. So with this strcmp, you can compare two different strings. If you compare these two strings, they are not the same. So the strings are either same, they're smaller, or they're bigger. So if you see the result of this string, you can see the str compare of these two strings, which was minus 23. If you look at the XYZ and XYZ, since they are the same, it returns 0. When you compare two strings, if they have exactly the same characters, the result of the strcmp will be 0. If one of them is a smaller or bigger than the other one, the result will be either a positive or negative. When you want to compare two different strings, the computer will compare them character by character. It will compare the ASCII code for each character. If all of the ASCII codes are the same, then those two strings are the same. If one ASCII code is different than the other ASCII code, it means those strings are not the same. It means that one of them is either smaller or bigger than the other one. With this strcmp, you can compare two different strings. With the strcpy, you can copy one string inside another string. When you say strcpy new text sub str, you can see the new text becomes xyz. So in this example, you can see that we're saying that sub str equal to ampersand string 1, 3. So when you do that, first, when you compare these two strings, you can see these strings are not same. One of them is different than the other. So we get negative 23. If you compare xyz and xyz, it returns 0. It means they're the same. If you say a sub str equal to ampersand string 1, 3, then you're getting part of that string 1. You're putting inside the substring. When you compare that substring with XYZ, it returns 0. It means with this code, you can get XYZ. So when you compare that with XYZ, they are the same. If you try to copy some string inside another string, you can use the strcpy, which will copy this as substring inside the new text, which this will become XYZ. We have also some C-string search functions like strchr, strrchr, str. So in these examples, you can see how we can use this. For example, when you say char org name 100, you're defining a C string of size 100. You're putting this string inside. When I say char new text 100, I'm defining another C string of size 100. With char star substring equal to null PTR, you can create a pointer that points to null. One of the functions that we have here is strchr. strchr source and search a character. It returns a null pointer if the search character does not exist in the source str, else returns pointer to the first occurrence. So with this strchr, you can look inside a string. And you can look to see if you can find a character inside a string. In this example, we say if strchr org name D not equal to null PTR. This will check to see if the D exists in this org name or not. We have another function strrchr, which returns a null pointer if search character does not exist in the source str. Else returns pointer to last or current searches in the reverse, since R is R and name. So with this strrchr, it means searching in reverse order for a character inside the string. If you could find that character inside the string, then it will give you the location. If it doesn't return, then it will say it does not exist. And if you search for this D inside this originame, D exists in this originame or not. When you call the strrchrd, it points to the last D. You could copy this substring inside the new text, which the new text becomes department. We have also str, which returns a null pointer if str2 does not exist in str. Else returns a character pointing the first character of the first occurrence of the string str2 within the string str1. With str, you can search for a string inside the string. When you say str org name div, it points to the first D. You can see if a substring is not equal to null, strcpy substring and new text. The new text now becomes department of redundancy department. So with str, you can search for a string inside the strings. If the string doesn't exist inside that string, it will return null. I want you guys to finish these activities. You can search and replace. There's an example in your book that shows how you can search and replace. So in this example here, I want you guys to study it, but we have an array of characters, which is a C string. We have a pointer to character, which is null. With the get line, you're getting a line. from the user, which it goes inside this C string, user input. But we have a maximum size of 100. So if the user puts hello exclamation mark, then you can use this strchr to find the position of the exclamation mark. You can say if the string position is not equal to null, star string position equal to dot. So it means if that position is not null, then put the dot there. We want to locate the BOO. We say str user input BOO. We put it in the string position. We say if a string position is not equal to null, then str ncpy a string position dash 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 3. It means you will find this BOO inside the text. You will copy dash 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 where the BOO exists. If you get a text like BOO whole, it will be dash 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 whole. It means you're replacing those with dash dash dash. I want you guys to study this section and finish all of these challenge activities. There is an example in your Zybook how to create a linked list. A linked list is kind of connection of different nodes together. So in this example here, you have a class, which is a class of int node. In this class, you have a constructor that the constructor will make the data in at 0. And then there is a pointer to a node that by default becomes null. We have insert after, we have get next, we have print node data. It has two different private variables. One of them is a private integer variable. One of them is a private pointer to a node. This means this is a pointer to a node. If you look at the constructor, in the constructor we have int node, which takes the data in it and a pointer. It points the data in it inside this data val. It points the next location in the next node pointer. It has insert after, which will insert something after that. It has the print node data, which will print the data. So in this example, you can see how you can create a linked list. If you want to create a linked list in C++, one way is to use classes. When you want to use classes to create a linked list, we can say int node star head object equal to node. This means I want to create a pointer to a node, and it's a null pointer. I can create 1, 2, 3 other pointers. I put null there. I can create another pointer, and I put null there. When you say head object equal to new int node -1, the new will allocate memory for a node. So this will create a node, and then this head will point to that node. When you say new node, new int node -1, you call in the constructor. This is the constructor. The constructor will take that -1. It will put that -1 inside the data. The next will be null. It means you will get a node that is pointing to a null. You can say node object 1 equal to new int node 555. Head objects insert after new object. This will insert another node after that node, which that other node is 555. You can say new int node to insert another node. Insert it after the node object 2. And then you can create another node, 777. You can insert it after the node object 3. If you want to print a linked list, you can say current object equal to head object. While the current object is not null, you can call the print node date. You can change the pointer to go to the next pointer by saying current object equal to current object get next. Get next means I want to get the next one. And then while this is not null, you keep going to the next one and then you print everything inside your linked list. I want you guys to study this and understand how the linked list works. There's an example here that shows how you can insert nodes inside the basic linked list. So I want you guys to study this and finish all of these activities. Your computer has different memory regions, so we can say a computer program's memory typically includes 4 different regions. We have a region where the computer instructions are stored, which is the code. We have the static memory, which the global variables, as well as static local variables that are located, are stored. We say the static variables are located once and they stay in the memory location during the program's execution. We have the stack, which there is a region where the function's local variables are located during function call. Whenever you have a function call, it adds the local variables to the stack and removes them. We have the heap, which there is a region that the new operator allocates memory. And delete operator deallocates the memory. This region is also called free store. We have different regions of memory. In this example, you see that we have some instructions. So the code, it has the instructions, like add R1, R2. The code region stores program instructions. My global is a global variable, and it's stored in the static memory region. The code and the static regions last for entire program execution. You can see this my global, which is a global variable, it goes in the static memory. Whenever you have a function call, it will push the local variables into the stack. Inside this main function, I'm creating my int and a pointer to integer. They go inside the stack. When main is called, the variables my int and my ptr are added to the stack. New allocates memory on the heap for an integer and returns the address of the allocated memory, which is assigned to my ptr. Delete deallocates memory from the heap. So you can see inside this, we have different memory regions. This my int and my ptr, they go inside the stack. With new and delete, you can allocate and deallocate memory, which the computer will use the heap for memory allocation. When you say delete, the memory will get deallocated from the heap. If you call myFCT, the stack will grow. It will push the function's local variables on the stack. These local variables are removed from the stack when the function returns. When main function exits, the main local variables are removed from the stack. So everything goes in the stack. When the program ends, everything goes out of the stack. I want you guys to understand different regions in memory. You could have this structure. We say this structure is a special class member function that is called when a variable of that class type is destroyed. When you have a class, you have a constructor, you can have a destructor. For example, a linked list class dynamically allocates nodes when adding items to a list. Without a destructor, the linked list nodes are not deallocated. The linked list class destructor should be implemented to deallocate each node in the list. With the constructor inside the linked list, we can create the nodes. With the destructor, we can deallocate and release the nodes. In this example here, we have this class. The linked list class has a pointer to the list head, initially set to null by the linked list class constructor. We have a pointer that is being pointing to null. When you say linked list star list one, you're creating a pointer to a node. When you say list one equal to new linked list, this new will create a new node. It will return the address of that new node. List one will store the address of that new node. After adding 2 items, 3 dynamically allocated objects exist. The list itself and 2 nodes. Without a destructor, deleting list 1 only deallocates the list 1 object, but not the 2 nodes. When you say delete and you put the list 1 here, list 1 is a pointer to a node. So when you do that, it will delete list 1. the objects will get deleted, but these two nodes, they stay in the memory, which is a problem. With proper implemented this structure, the linked list class will free the list node. If you have a linked list that it has a destructure, when you use that linked list, when you're done, you're deallocated, it means you will remove those nodes, which we call it allocation and deallocation. If you want to implement the linked list class destructure, this is how you can do it. You have a class of linked list node. It has a public constructor that takes an integer variable. In this constructor, you're printing the data value. You're putting the data value inside data. And the destructor, you say cout, and the destructor, you cout the data. So you have data, and then you have a pointer to a node. In this class implementation, you have a constructor, and then you have a destructor. So we have a prepend function. In the constructor, you're putting null pointer inside the head. It means your head is pointing to null. And the destructor, you say while head linked list node star next equal to head next. Delete head, head equal to next. In this example, you can see that the structure deletes each node in the linked list. This head node, it means the next one. So you have a pointer to the linked list. This will give you the next one, and then you keep deleting the head, and then you put the next inside the head. It means for each node inside my linked list, delete and release the memory. This is the definition of the destructure for the linked list. It means it will deallocate the memory for all the nodes inside the linked list. In the prepend function, you're saying linked list node star new node equal to new linked list node data value. With the new operator, you're allocating a list and you're creating a linked list and you're putting this new node there. And then you say new node next equal to head. You're changing the pointers. You say the head goes inside the next of this new node. And then the address of the new node goes in the head. This will prepend an element, your linked list. This will create a node. This will put the head inside the next of that new node. And then the new node will go to the head. It means it will prepend an element inside the linked list. I want you guys to finish these activities. Using the delete operator on an object allocated with the new calls the destructor. If you say delete and you try to use delete on a linked list, it will call the destructor. So for an object that is not declared by reference or by pointer, the object's destructor is called automatically when the object goes out of scope. In this example here, you see that we say linked list list one. This is an instance of this linked list. I'm prepending one. And then I'm returning the 0. I want you guys to finish these activities to see how the linked list works. I want you guys to finish all of these challenge activities. Sometimes we have something that we call a memory leak. Memory leak, the memory is leaking. It happens when a program that allocates memory loses the ability to access the allocated memory due to failure to properly destroy or free dynamically allocated memory. So sometimes when you work with the memory leak can happen. The memory leak can use up all of the available memory. In this example here, we say while expression, allocate memory for new val, do something. So memory is allocated for new val, each loop iteration, but the loop does not deallocate memory once done using new val, which it will result in the memory leak. We have two problems here, which one of them is the memory leak. Memory leak means you're leaking memory. So when you work with pointers, you have to be careful. If you don't use them right, these issues, they may happen. We say a program's leaking memory becomes unusable. Like a white water pipe might have water leaking and becoming unusable. When the memory leaks, it's wasted. There's a common error that is failing to free allocated memory that is no longer used. Whenever you allocate memory, remember to deallocate it. If you say new, remember that you need to have delete. Many programs that are commonly left running for long periods, like browsers, they suffer from known memory leaks. So be careful. We have something that we call a garbage collection. Some programming languages like Java, they have a mechanism which we call a garbage collection, where a program's executable includes atomic behavior that has various internal. Garbage collection means the computer will deallocate the memory that is not in use. So these high-level languages like Java, they have some mechanism that if there's any memory that is not being used, they would collect it and then they would free that memory, which we call the garbage collection. So I want you guys to finish this. I want you guys to study this. Whenever you have a constructor, remember to add a destructor. Whenever you allocate memory using constructor, remember to deallocate memory using destructor. In this example here, I have a class. It has a public my class, which is a constructor. It has a private pointer to an integer. Inside the constructor, I say sub object equal to new int. I'm allocating a sub object. I say star sub object equal to 0. I'm putting 0 inside where this pointer is pointing to. Inside my main function, I say my class star temp class object. I have a pointer to a class. I say temp class object equal to new my class. I'm creating an instance of this class and I'm putting it here. If I say delete temp class object, I would have memory leak. Because I'm trying to free a memory, read objects memory, but not sub objects. So in this example here, you can see how the memory leak happens. When I say new my class, I'm creating an instance of my class. When I create an instance of my class, I'm creating a new integer, I'm putting in sub object, and I'm putting 0 inside that pointer. When I delete the temp class, I'm freeing the object's memory, but not the sub object's memory, which it will cause and it will lead to a memory leak. So you can see this temp class object is a pointer to object of type my class. New allocates memory for the objects. The constructor for the my class is called the constructor allocates for int using the sub object. If you say delete temp object class, frees the memory for temp object class, but not sub object, which a memory leak will happen because memory location 78 is still allocated. But this is an example of a memory leak and how it can happen. Whenever you work with a memory, remember that if you allocate memory for something, you should deallocate it at some point. We have something in C++ that we call a copy construction. You could copy an object without a copy construction. This animation shows a typical problem that arises when an object is passed by value to a function and no copy constructor exists. In this example, see that we don't have a copy constructor. We have a class, my class. It has a public constructor. It's this constructor is displaying the constructor called data object equal to new int star data object equal to 0. So the constructor is just creating an is putting 0 inside what this pointer is pointing to. This is the destructor that the destructor will delete this data object. The data object is a pointer to integer. We have this a set data object and get data object. The set data object will put the I inside where this pointer is pointing to. The get data object will return what data object is pointing to. We have a function here. When I say my class, temp class object, I'm creating an instance of this my class. With the set data objects, I'm setting the data object to the 9. When I say get data object, it will display 9. I have a temp class object that it has 9 inside it. When I say sum function temp class object, I'm passing this temp class object to my function. This function is taking an instance of my class. So when that ends, the destructor is called. The memory, when you call it destructor, the memory gets freed. After the destructor is called, if you call the get data object, it will display 0. In this example, you can see how you can copy an object without a copy constructor. But your program will crash because finally when the destructor is called, there is nothing there to free. And then the program crashes. In order to solve this problem, you can create a copy constructor. We say a copy constructor is a constructor that is called when an object of a class type is passed by value to a function, and when an object is initialized by copying another object during declaration. For example, if you say my class object 2 equal to class object 1, or if you say object 2 ptr equal to new my class object, the copy constructor makes a new copy of all data members, including pointers, which we call a deep copy. We have two different things here. One of them is deep copy. One of them is shallow copy. If you want to use the copy constructor is the constructor that copies one class inside another class. How we can create a copy constructor by defining a constructor that has the same name with the class, and it takes an object of a class. So in order to create a copy constructor, we create a constructor inside our class, which in this example, we have this copy constructor. This copy constructor takes an instance of your class. In this example here, you see that we're saying data object equals to new int. I'm allocating a new integer and I'm putting that inside the data object. I say star data object equal to star orig object dot data object. It means I'm copying this data object from this original object into this data object, which this is the definition of the copy constructor. If you don't use a copy constructor, then you will not be able to create a deep copy of an object. A deep copy of an object means when you have a class, that it has a pointer variable. If you try to copy an object of that class inside another object, this pointer may not get copied. In order to include this pointer variable inside your copy, you need to define the copy constructor. And in the copy constructor, you have to specify what are you copying where. It means in this copy constructor, I'm allocating an integer and I'm saying the data object of that original object, I'm dereferencing it and I'm putting a data object. This is copying that variable inside this variable, which it would create a deep copy. So with copy constructors, you can create deep copies of objects. If you create a copy of an object by copying only the data member's values, we will call that shallow copy. A shallow copy is fine for many classes, but typically a deep copy is desired for objects that they have data members pointing to dumbly allocated memory. Whenever you're dealing with the pointers, it's good to create a deep copy. If you just have a class that has some variables, there are not pointers involved, then you can create a shallow copy. With a copy constructor, you can copy one object inside another object. If you say class object 2 equal to class object, or if you say object 2 ptr equal to new my class object, You're creating a new object and I'm putting it inside an old object. It means I'm trying to copy one object inside another object, which the copy constructor will do that. It will copy one object inside another object. I want you guys to finish these activities. We also have copy assignment operator. Given two my class objects, class objects 1 and class object 2, a programmer might write class object 2 equal to class object 1. To copy class object 1 to class object 2, the default behavior of the using assignment for classes or structs is to perform member-wise assignment. If you say one class equal to another class, by default, the computer will copy each variable inside one class to another class. In this example, I have a class. I have a constructor, I have a destructor. I have set data object, I have get data object. I have a pointer to integer. In the constructor, I say data object equal to new int. This will allocate a data object. I say star data object equal to 0. This is the constructor. I have the destructor that in the destructor, I delete the data object. If I say class, the class object 1, I'm creating one object of this class. If I say class object 2, I'm creating another object of the class. With the set data object 9, I can set the class object 1's attribute to 9. When I say class object 2 equal to class object 1, I'm using the equal to copy one object inside another object. When you try to copy one object inside another object, the compiler will copy the variables inside one of them into the other one. If you call the get object for the class object 2, it will display 9. It means you're having member-wise copy of the variables inside one object to another object. You could overload the assignment operator to create a deep copy. How can we do that? In this example, I'm overloading the assignment operator. I say my class ampersand operator equal const my class ampersand object to copy. If you look at the definition of this, I'm saying if this is not equal to ampersand object to copy, delete data. If this is not equal, delete data object equal to new end. This will delete the old object, this will allocate new object, and this will copy the data object of one object inside the data object of one object to the other object. It means it will copy the data object, and then you return this. This is the definition of how you can overload the equal. It means when you use the equal, when you say class, my class object 1, class, my class object 2, when you call the set data object, the data object becomes 9. When you use this equal, the compiler will create a deep copy of the object by definition of the overloaded equal operator. It means you're creating a deep copy of an object inside another object, which this is the definition of that equal, which you have overloaded that equal operator. I want you guys to study this, finish all of these activities. Chapter 8 has some examples of lists using vectors. I want you guys to finish them. There is section 11.12 that talks about rule of 3. Classes, they have 3 special member functions that are commonly implemented together. Destructor, copy constructor, copy assignment operator. We have this rule of 3 that describes a practice that if a programmer explicitly defines any one of these 3 special member functions, then the programmer should explicitly define all 3. If you define any of them, then you have to define all of them. This is rule of 3. Those 3 special member functions are sometimes called the big 3. Destructor, copy constructor, and copy assignment operator. I want you guys to study these. There are some labs in this chapter that I want you guys to finish. I will assign this chapter, chapter 8, If you have any questions, I have office hours tomorrow. You can come and ask me questions.